differential equation 和那个第三个。
I'm glad that most of you are back. So we are very happy to have our first speaker in the afternoon, Y.P. Lee from University of Utah, who will talk on this part.
Okay. So this was an original plan, sort of more or less dictated by Davish. So, but then he and we coordinated a little bit about what he should be talking about, but he sort of fell short on his promise. I'm not sure I can cover this much ground. So that's the plan. So the plan is to talk about some kind of framework which enable us to talk about the last two applications. And then he also told me that the talk doesn't have to be very updated, and doesn't have to be very specific, but has to be inspirational. But that's very high order, so it's very tall order to reach. So but definitely I will not be very specific, and it's going to be very vague. So if you have any question, something is not clear, let me know. And I probably won't write down a lot of formulas because any of these formulas is extremely long. So I'll just sort of do things schematically. So the first part of the goal, in order to reach there, sort of a motivating question is, so we've been talking about this moduli space. So you use moduli of stable maps, and then use this to sort of create the Gromov-Witten theory, definition of Gromov-Witten theory. And that's modular stable map also mapped to moduli of curves in GN bar. Then one can ask, what about this moduli of Gromov-Witten theory? So one can ask, so if there is some kind of moduli, can I describe some kind of parameter space of Gromov-Witten theory? And this is actually, this is certainly, if there exists one, it's definitely not going to be finite dimensional, because if for every different varieties, they usually get different moduli spaces, and then you have varieties of all sort of types. So this is going to be some kind of infinite dimensional thing. Nevertheless, there is some kind of structure which I will describe about this. And so this is sort of a heuristic will involve here. Before I can, and the reason, even though this is infinite dimensional, can give some structure, is because it's sort of modeled on this moduli is sort of modeled on. So there is some kind of infinite dimensional Lie group, or some kind of quote unquote algebraic group acting on this scalar quote moduli of Gromov-Witten theory. And so using the structure on this group, we can give this module some kind of structure. And that's what we're aiming at. So before I can say that, let me give some kind of framework of this what I call geometric Gromov-Witten theory. So what's the input data of this is really, so you have a vector space, And you can do this over Q, but I'm just going to over C, just make things a little bit easier, so I don't have to worry about 2 pi I or things like that. So I have this vector space, and on this vector space, there is a specific vector which we call 1, and that's the identity vector or fundamental class of this X is, let's say, it's complex projective, non-singular projective variety. And so I have a specific vector inside this vector space, and this vector space is endowed with a non-degenerate pairing. Let's say symmetric. And so to say symmetric, I'm sort of maybe I should say even. And if it's not, if you take in R classes, you have to consider Z2 graded kind of thing David already alluded to. So I won't say too much about that. But theory can be extended that way in most cases. So you have this input data, and not just that, you have then you have so from here I'm going to think about what. So you remember David has this insertion. So your insertion, this is sort of your for each mark point. This is sort of the space of insertion. Space of your insertions. So the class you can stick into your Gromov-Witten invariants. But the theory which works better is the following. So in fact, I'm going to increase this space of insertions by consider the psi classes, which so David didn't mention. He deliberately skipped this. So what are the psi classes? These things. Let's first think about modular of curves. And for modular curves, you have a universal. Well, if you consider this somewhat as an orbifold, as a stack, then there is a universal curve. And because this curve is n-marked, so this universal curve would look like, if you consider a specific element here, it's going to be a curve, a class of curve with n mark points. I'm using David's notation. The x1 to xn are mark points. And these so that's what you see as your fiber. And so these mark points give you n sections of this curve. And so let me call this pi, because the fiber is actually only nodal. So this is actually pi is local complete intersection. So the relative dual sheaf of this map is actually a line bundle. And you can take this, and so what are these psi classes? Psi I is just xi for back omega pi. In other words, these are sort of and because from the definition that these points will never lie in the singular locus of this curve. So this is actually in fact, wherever this section lies, the curve is going to be smooth. So this is more or less the same as your if you like to think about your cotangent bundle of this at ith mark point. That's the fiber of this. So these are sort of divisor classes on your modular of curves, and you can also insert these into your modular insertion space. So I'm going to increase the insertion space. So I'm going to beef up my insertion space. And I'm going to put the T here for a reason which will only be clear later. I'm just going to define this as infinitely many copies of my original insertion space And I'm thinking about this as the basis. So if this phi mu is a basis of my original insertion space, which is your even cohomologies, this basis is going to be phi mu and then psi to the k. And depending on which point you're inserting this, you put psi I, etc. And the phi mu become EVI pullback. Is that clear so far? So I'm just taking this theory to include this, and this is what if we don't have the psi classes, as David mentioned, it's called primary. With psi classes, usually called descendants, for the reason which seemed to be clear to physicists. They start with primary and then they create descendants. So that's and then so you can talk about this genus G. So then your Gromov-Witten invariants, you can have these Gromov-Witten invariants, which each insertion. So I'm going to use this notation, ball phase T, to be arbitrary. So and I can insert each one of these into my, so this is the genus G generating function of all, so we call it descendant Gromov-Witten invariants. You can code everything into this function. Sum of all beta in your effective curve class, and sum over all n. And then you take this in genus G, and you have n of them, n mark point in beta, and you divide it by n factorial. And you see that this gives you all the Gromov-Witten invariants by taking the coefficients. For example, if you think about the coefficient, so the coefficient of T mu 1 K1 up to T mu n Kn. So this will be something like, say, so this guy, you will have to, because these are all linear in your T variables. If you want this power, you will have to go to, so this might not be a good, so m. So this will only lies in n equal to, as n equal to summation of mu I, right? And then sum of, oh no, sorry, I confused myself. Okay, so this is lies in n. Yeah, I was right. So this lies in n. So this means I have some kind of phi mu 1 K1 phi Kn. And then David mentioned some kind of a completion by Q, so nomical variables. Are suppressed here. So I won't, they can be recovered by some procedure, but I will just constantly ignore the nomical variables. He talked about completion by this capital Q variables, which you also constantly suppress them. And they can be sort of recovered, but so these things might not make sense because when you sum it all up, it might not even be a formal power series. So that's why usually you have this Q to a beta here.
What is the phi mu sub k? Is that, do you mean like side of the k?
Oh yeah, yes. So yeah, so that one, yeah. Sorry. Yeah, thanks. And if so I don't know why. all this tape recording make me very nervous. Okay. Anyway, so any other questions? And so far I just say, what I said so far is just to encode all these information in some kind of a setting. And now, and what's this? So this is just sort of formal way of stating things. It really doesn't do too much, but let's try to reformulate this in a different way. So yeah, so as I said, in order to know all these descendant Gromov-Witten invariants, I just need to know this function, this one single generating function. And as I said, I'm going to strike this out. So I'm going to constantly ignore this. This will be just dropped from the notation. And that sometimes make this expression nonsensical, but you can make sense of it somehow. That procedure I will ignore. Okay, so I will reformulate this in a different way. So, and you can. So I'll introduce it. So let's sort of exit. And to give axiomatic approach, I will first say it's differently. So, okay, so as David talked about, this moduli space of stable maps actually map to moduli space of stable curves by forgetting the map and then stabilizing, right? And you can further you forget mark points. You can go to GN. So that's very common procedure. You can deal with this. And so that means if you have any relations in MGN, that relation pull back to the relation in MGN plus M x beta, and therefore give a relation on, so any relations in Gromov-Witten theory. Right? So any relations MGN will give you a relation in Gromov-Witten theory. For example, David just mentioned, for example, if you have, he used this to prove the associativity of P2, a canonical module of P2, right? So he said, well, if you have this 4 plus M mark points, you can map that to M0, 4, and here every points are rational equivalent or homologous. And you pull back two different points that give you a relation in Gromov-Witten theory. And these are universal in the sense that it's target independent. For any target, the same shape. So and a couple of these relations are the following. So David mentioned the associativity relation, which come from the fact that M04 bar is P1. But there are a couple more relations. For example, this so-called string equation. String equation is very simple thing, which I'll say very quickly. If I have this is morphism of, this is forgettable morphism. I'll call it still pi. Just forgetting the, let's say, forgetting the last mark point. That means I have a curve here, x1 up to xn plus 1, and I just take this class and map to, I take that, and I forget the last mark point. And then if by forgetting the last mark point, the curve becomes unstable, I have to stabilize it. Okay, so that's very common. And so what can we say about this? Well, there is a relation between the psi classes upstairs and downstairs, because the psi class upstairs is not the same as pullback of psi class downstairs. The ith psi class is not the same as I downstairs, but they differ by a divisor. So this is divisor, pullback is divisor, so they different differ by divisor, and this divisor is the following. Sorry. So plus a fixed divisor. This divisor can be described as a boundary divisor of this MGM plus 1, as saying that the ith mark point and then m plus first mark point and the rest here. Furthermore, you can see that this psi I, m plus 1, because this guy, when I restrict, let's call this divisor in moduli, I call it di. So this, when I restrict on di, it's actually trivial, because you see this, I'm talking about the ith mark point, but ith mark point lies in a three-pointed moduli space, right? This is like M03, of course, something else, but anything on M03 bar, which is a point, is trivial. So this, and from here you can get some relation about this. For example, you see that from here you can deduce I from 1 to n, and I insert nothing for m plus 1. So this is only up to n, not m plus 1. So, and if this were pulled back by projection formula, you get 0, because the fiber dimension is 1, while these things are pulled back, so you should get 0. But these are not pulled back and differ by these. And by these two equations, you'll get, this is exactly summation j from 1 to n. So these are in m plus 1. And then this will go down to summation, and each one of them be psi I ki minus delta ij. I don't know, is that correct? Yeah, I think that's correct. And these psi i's are in n. These are psi i's are in n plus 1. I don't know. So that's so that's what usually called string equation. And these equations have also can pull back to Gromov-Witten theory. So far, I'm just stating obvious things, and then there is so also similar things which I will not say too much. There is called Dirichlet equation, which also is kind of simple. If you ask what the same setup, and you say, well, because this guy over this is of fiber dimension 1. In fact, this is isomorphic to your universal curve. So what's the number I will get by integrating the divisor? For example, this is what's push 4 of psi m plus 1. So I take this guy has no psi m plus 1, but now what if I just push 4 psi m plus 1? What would you get? Well, but we know psi m plus 1 is almost the same as the as your relative cotangent bundle, except that this. So this will be twisted by your sections. And so this is, so, well, again, integration over fiber, you get 2g minus 2 plus n. This is, so that's, so in fact, you can do this a little bit better than this if you let me do. So if you take any product of psi I, ki from 1 to n, and then with one of these, and then you will get just the same as modify all these times product. So this relation can be pulled back, and then plus another relation. Usually, this is only true in genus 0, called topological recursion relation. And basically, it says the psi class on M0n is boundary. It's a boundary divisor. And what is this boundary divisor? It's one presentation you can take is to pick 2 more mark points. Let's call it J and K. And then psi I will be the same as boundary. You have, and so let's say I, J, K, union I is the same as 1 to n. And then then I can write this for any J, which is subset of I. Then you can put J here and J complement here, and summation over all J, which is a subset of the complement IJK. And also make sure this is stable. So here, for example, you need at least put 1 point, but here J complement can be empty. Is that clear? So that's just three equations you can get. And so the last equation only true for genus 0. For genus 1, there's some kind of a similar statement, but for higher genus, this is simply untrue. Yeah, sure.
Explain why the dilaton equation with the psi classes, as you stated, is true. The psi's don't pull back, right?
Yeah, the psi don't pull back. So you have to use the fact that the psi doesn't pull back, but when you have this. So the last, if you use the psi n plus 1, when their difference, when they restrict on difference, actually trivial. So I mean, it's a bit of work, but
that's not just full formula. You have to check.
Yeah. So it uses the fact that the psi n plus 1 also, on this component actually will give you true. Does that make sense? Mm-hmm. So this axiomatic genus 0 theory. So as I said, any Gromov-Witten invariance for genus 0 is just determined by genus 0 generating function on this space, right? It's given by this guy, which is a function. Is take the t is in your HT, this infinite dimensional vector space, and which so this any of these which satisfies these 3 equations. And this is only in genus 0, although I wrote these for higher genus for first 2, string equation, dilaton equation, and topological recursion relation. And that's what we call axiomatic genus 0 theory. And so, and as I said, if this comes from some geometric Gromov-Witten theory, it certainly satisfies these 3 because from the construction, any relation moduli space of stable curve pull back to moduli space of stable maps. So that's and what I stated here is also usually not completely what people talk about, because they will reprove this on moduli space of stable maps where the psi class is not pulled back of this. So I'm sort of mixing these 2, but nevertheless, yeah, with given time, that's the best I can do. So it's a little bit vague, as I promised. As I said, I will definitely do it not very specific. I'm not sure it's very inspirational. Anyway, so and what's the use of this? So far, I'm just framing things. I define something which is include everything discussed geometrically. But what's the use of this? So the use of this is that I'm going to consider slightly different framework. This slightly different framework is I will include this, and this HT I just said is actually the direct sum of all H. I can think of this as H of this. And I'm going to double this. I'm going to consider, so I'm going to consider the space which is somewhat defined as the Laurent series, and in Z inverse, which you can think of as the cotangent bundle of H. I'm going to just use shorthand notation. Right, so this is. So from this space, I add its cotangent space, so the dual space. And the good thing about this is that, as we know, the cotangent space any cotangent space has a symplectic structure. That's what we're looking for. So we'll call this symplectic structure omega.
Let's call it.
And this symplectic structure, what's the good thing about this symplectic structure? So then I can define something which sort of this is defined to be this is matrix valued Laurent series in the inverse. Such that this is a preserving the symplectic structure. Meaning that if I take two vectors here, so this H, if I take two vectors in my H, and then this omega of Fg is the same as omega of MFG. So abstractly, one can also say that that this group acts on the axiomatic genus zero theory. So that means I have to check if I take that and take that group acts on my that acts on my this theory, would that preserve these three equations? And it actually does. And specifically how it acts, sorry, so I won't say too much about this, but this acts on the space of genus zero theories. And how do you think about this group? And this group is more like, you should think of this, some kind of a twisted, this L2 GLH, some kind of a twisted loop group. Loop group in the sense that it's sort of a Z and Z inverse. Somewhat, think of this as functions on C star. So that's your loop group. And preserving the symplectic structure, that's why it's twisted. It's not just the loop group. If you just consider endomorphism value, Laurent series in Z inverse, that more or less the sort of a loop group, then I want this to preserve symplectic structure. That's where this twisting is. The symplectic structure. So okay, now that we have this, so yeah, I should mention this is and in fact more is true. So maybe I should mention this. So the theorem of Giventhal is that this axon space of, and then this is, and furthermore, this action is, it acts transitively on semi-simple theories. So, so I should explain what semi-simple theory means. So a genus zero theory is called semi-simple. If the corresponding quantum, so this is actually, unfortunately, I have to use big quantum product. Is semi-simple. Meaning that, you remember, because I'm only talking about even classes, and so this is a commutative associative C algebra. And semi-simple just means you can find a basis, so existence. So equivalent definition of this is, for example, for every vector in H, if you quantum product itself many times, it's never going to be equal to 0. No nilpotence. In the quantum Coleman. Or there is another thing says under the quantum product, this actually there is idempotence, meaning that you have a basis such that phi I star phi j is actually and the only thing which is cohomology. So cohomology is if you don't talk about quantum cohomology, but only ordinary cohomology, this usually is always nilpotent because if your degree get too high, it's always 0. Except this is as nilpotence, except when X is actually union of endpoints. Right? So if X is union of endpoints, then you take any point as your basis. So phi I is just the fundamental class of the ith point and then certainly it satisfies this condition. So that's the only case when it's semi-simple for non-quantum. But when you deal with quantum cohomology, a lot of things are semi-simple. And example of semi-simple theories are so if, for example, X is equal to any toric, or X is a homogeneous space. Or in this case, when you deal with this sort of so miniversal, so this axiomatic theory from the miniversal deformation of AD singularity. So anyway, so there are a lot of semi-simple theories. Okay, so if we know that any two semi-simple theories can be obtained from one from the other by by the group element. So to know the theory, it's to know if I know one theory and I don't know another theory, I just have to find the group element. And so but you know the group element here is some kind of loop group. So and loop group is heuristically you have this sort of Birkhoff iteration. So tells you that your can be factored into some kind of sort of holomorphic in the disk at infinity and holomorphic in the disk at 0. So that's heuristically what happened. Okay, so and then there is also the fact that if know the quantum product, then I can get the S inverse and R by some easy inductive procedure. And by easy, I mean it's actually doable. It's not like in principle doable. It's actually you can just compute that. And in a good case, usually you get closed formula for project spaces, for example. So these things you can actually calculate. And which shouldn't be surprising because, after all, these is going correspond to what they should encode the same information as that. So as I said, since I can okay, so as I said, I can take from one point to another, and the easiest Gromov-Witten theory is when X is a point, right? That's certainly the easiest one. So which David mentioned. So in this case, the Gromov-Witten theory is just, so when X is a point, then your modular space of stable maps can only map to degree 0. And in this case, because this is also a point, this is just the same as MGN. And so you want to talk about all the Gromov-Witten theory and MGN, which is this is sort of a Witten's conjecture. But because I start with H, which has rank n, then so I can beef it up to, in this case, I can beef it up to m points, as I just mentioned over there. I can talk about m points. And so in that case, your H become rank n, as I explained over there. And so the Gromov-Witten theory just tensor product all these n copies of Witten conceptual theory. So which is well known. Okay, so we can start from here. So this is our reference point. Now I start with this, and then if you start with this theory of n points, and then to get your genus 0 theory of any arbitrary x, I just have to find my S of x and R of x acting on this theory. Right? So this will give me this. And what we said is this is true in genus 0. And so what if because this theory in genus 0, I can get in genus 0. What if I want this to be in all genus? And this is the result of Giventhal and Tellerman proves the general case. Giventhal conjectured and proved some cases. Tellerman proved the general case is that this actually will also work in all genus. And so the formulation is, in one formulation you can do is the following. And you have to, but in this case, you have to quantize this. Then you get, in this, here you get that's for your x. So if you quantize these two operators, there is a specific procedure how to quantize these. Maybe I'll give you a reference of this. But you can quantize these and get your higher genus potential. And this is definitely very, so what they're saying is, in fact, to know if your X actually give the semi-simple theory in genus 0, then all higher genus Gromov-Witten invariants are practically determined by genus 0 Gromov-Witten invariants and the higher genus theory for a point. So that's this theory is about. In fact, sort of more precisely, so this actually given slightly so additional structure, some kind of a slight additional structure. This the choice of this R is unique. Although I won't be saying too much about that. And they're also constructive too. So now what can I say about the two applications I promised? Well, I'm late for 10 minutes now. So one thing we know is the Witten conservation theory for a point or moduli space of stable curves is equivalent to can be described by something called Virasoro constraints. So Li on tau point, so this is what we call tau endpoints. Li equal to 0 for every I from -1, 0, etc. And this is called Virasoro because these Li satisfy Virasoro commutative relations. And so to prove, so it was also conjectured for any x, you should have also the Virasoro conjecture. And what this formula is giving you is the following. So let's think about this. And so we know that if L tau endpoints or n copy of this is equal to 0, that's what we know, right? And so what about this? So what about if I take S hat, R hat acting on tau endpoints? Can you get some L, make it equal to 0? It certainly can. What you can do here is the following. So I can take this Li. What I can do here is I can take Li, and I can take the inverse of this. This is certainly equal to 0. This implies this equal to 0. And so because it's conjugation, it satisfies the same computation relation. This you can call it Lix. Lix also satisfies the Virasoro commutation relation. In fact, this is the same as the usual Virasoro. This is the same as the Virasoro operator. Defined by Eguchi, Hori-Shion, and Sheldon-Katz. So that's so this is give you a quick way to prove Virasoro conjecture when X give you a semi-simple. And so this check-in is not particularly hard. You can actually do it. And I think we did it in our sort of stillborn book. So in part 2. Okay, so that's one application. Another application here is that since, okay, so for semi-simple theory, we know R acts on that. So so this is, you can, as David mentioned, you can, so just for the simplicity, I use sort of a numerical version of these. Everything is function, but you can use the cohomological field theory formulation, and everything still works. You can take the same, so in fact, that's Tellman's small generalization of given task formulation is to sort of beef this up to cohomological field theory. And so there you can still say that, okay, so the second application I was talking about was to how does this help me to get, so we're saying the following. So we're saying any relations in modular curve give me some relation in Gromov-Witten theory. For example, concepts use this very simple relations of any 2 points in P1 are rational equivalent to prove, to give the count of rational curves of degree D pass through 3D minus 1 points in P2, right? So that's very simple application. Just use the relation in modular space of curve to give the modular space of stable maps. So, but the last application I'm going to mention is going the other way around. So suppose I know something on moduli space of stable maps. Can I give some relation in moduli space of curve? And so that's another way. So okay. So application 2. It's so this framework gives relations in MGM, cohomology MGM. How does it give that? So the idea is actually quite simple, but you have to find correct examples to make this idea work. And maybe there are other good examples which hasn't been used. For example, that this is so I think Rahul Pandaripande and then Aaron Pixton. And then Dmitry Svankin. They pick the following theory. They say, okay, so suppose I know the axiomatic theory of AN singularity, which it's not mentioned here, unfortunately. So, but I'll just put that into a black box anyway. And so this is also create the same as some people call n+1 spin curve theory. And so what in this theory is so this particular theory, genus zero theory, is very easy to compute. You can compute genus zero theory very, very easily. It's much easier than, for example, the quintix threefold mentioned this morning, and it's just very easy to compute. So, and once you can compute genus zero theory, then you can get this R matrix we're talking about, right? But just from the construction of this higher genus theory, it's very difficult to compute. But we know some kind of dimension, expected dimension. We know expected dimension. So, and just knowing this, it's enough to give us relation. And so what I did is the following. So let's say, okay, let's take this endpoint. So this AN. Let's see. Do I get the number right? Yeah. So AN. This n corresponds to my dimension. So maybe this n should be this capital N. Right? So what I said is, okay, so now I take tau function for endpoints, and I apply this R matrix on that. I should be getting, because you remember this R is obtained from genus zero theory by some procedure called quantization, which I didn't explain, but it's not hard to write down the quantization. So if you do this, then this should be giving me some tau function for AN singularity or n+1 spin curve. But what happened is they know the expected dimension, and these things, when you act on that, it gives you something which go beyond the expected dimension. So if you phrase everything in terms of This is in sort of invariant form. But if you take cohomological field theory, which is easier to get this kind of formula because you actually keep track of a dimension, which you live in cohomology of MGN, right? And so some classes here in action by R matrix and goes to cohomology of here, and so they should have lived in some expected dimension. But actually, it has classes in all dimensions if you apply this formula directly. And so what happened here is, oh, you know that anything beyond the expected dimension, which is not in the expected dimension, should be 0. And this actually proves the Pixton. So this sort of prove this actually go into this sort of acting on this cohomological theory relate to endpoints give me this, which is not in the expected dimension. In fact, give you all the. So this proves the Pixton conjecture or Pixton generalization of Faber and Zagier conjecture. In cohomology, and because they had to do this because they use Tellerman's classification, which only true in cohomology. And what Rahul's student Yangda did was to say, if he phrased this differently, so he said, okay, why do we have to do this? He did this for stable quotients to P1. And then and what he used also similar to this, he just said, if I do a stable quotient for P1, and then I know the original theory has to be in equivariant class globally, so it has to be in terms of equivariant parameter, it's being polynomial ring of equivariant parameter. But you do localization, you see a lot of things which should have been 0, because if you sum it up, it should be in the polynomial ring, but now you're in a fractional ring. So anything which is in your equivariant parameter, say called lambda inverse should be 0. It's just from the speed. So if you organize that correctly, you also get this. And then when I suggested him was to think about this not in terms of sphere quotient, but Gromov-Witten and P1, equivalent Gromov-Witten, and he did it. And in fact, he generalized this to any Pn. So just from this, you can get this kind of a simple idea. You get this very so for example, this proves again the Faber and Zagier's conjecture by restricting to open part. Oh, I'm already over 2 minutes. Thank you.
Questions for YP?
It's a lazy question. Why is it called the string equation?
Well, yeah, so it's called string equation because it's equivalent to string equation in a different theory. So it should have been called puncture equation because you sort of put additional puncture, which you put nothing there. So in sort of topological gravity, it's called puncture equation, but it's equivalent to something equivalent to topological gravity in different kind of setting, doing some kind of triangulation on the metrics and more related to inequal system. There has more sort of a properly named string equation. That's my understanding. I don't know. Yeah. Yeah. So yeah. So.
Thank YP again.
Oh, sure.